All right, this is the intro video for AP Calculus AB section 5.4. We're going to be looking at the derivatives of exponential functions as well as some integrals of exponential functions. Okay, so in class later on I think I will do a little proof of this for you, but for now we're going to talk about the derivative of e to the x, and so the derivative of e to the x is e to the x, perhaps the easiest derivative of the year to remember. Or if it happens to be a composite function where the exponent is something other than an x, then we would say d dx of e to the u is equal to e to the u times u prime. Oops, let me get that in the right spot there. There we go, u prime. Okay, so maybe if you recall the graph of e to the x could be helpful in understanding how this works. The graph of e to the x is a curve, an exponential curve that increases steadily from left to right. But of course, as you go further to the right, the curve continues to steepen. So the bigger the x value, the bigger the value of the slope, and that fits with e to the x, and it fits with other things as well. But like I said, when we get into class, do a little proof of this for you. Hopefully that'll make sense. But for now, if you don't mind just accepting that d dx of e to the x is e to the x, we'll be able to move forward and hopefully get some things down here on this video. So let's take a look at a few examples here. Number one, g of x equals e to the 8x. We're supposed to differentiate. And so this more fits the e to the u, right? Because the exponent is not just a simple x, it's an 8x. So here's how this would go. G prime of x equals e to the 8x times the derivative of the inside, so it would be times 8. That chain rule factor is what that 8 is right there. So you can see it's just e to the u times the derivative of whatever that u happened to be. All right, let's go ahead and move on to our next example. Okay, so with number 2, once again we can see that the exponent is more complex than just a simple x, and so we're going to have to use that chain rule version of this. So we're differentiating, so we're going to write f prime of x is equal to e to the exponent. The exponent doesn't change here, so e to the 3x squared minus 8. But then we've got to multiply by the derivative of that inside. So the derivative of 3x squared minus 8 is 6x minus 0. Or of course, we could just write 6x. And that's it. That's it. We're done with that derivative. Okay, so as you can see, we're going to skip a little bit ahead here. The video is going to continue on down below, so go ahead and jump ahead with me. So now we're going to look at the integral of the e to the x function. So I'm guessing you can think this through perhaps. If the derivative of e to the x is e to the x, then the antiderivative of e to the x would have to be e to the x. So we'd write e to the x plus c right here. And then if you're integrating the same sort of thing, except the exponent is a little more complicated than just an x, we'd consider it a composite function, and we'd have to consider, do we have exactly the right pattern? And so we'd have to consider, is my du the correct du? So if truly that du is exactly what it should be, then we can just write equals e to the u plus c. Of course, there might need to be some adjustments made to that du. We might have to multiply by a constant or something to make that du correct, and of course it requires an adjustment on the outside of the integrand as well. Again, it's the u substitution or Timmy messed up the chain rule concept that we've talked about in the past. Okay, so let's work on a couple of examples here and we'll be done. Okay, so number 1, it's the integral of e to the 3x plus 1. We can see that the exponent is got more going on than just an x, and so we have to consider the chain rule here. So what we want to look at is, we want to ask ourselves, is the derivative of the exponent part of the integrand? This would be looking for a pattern here. We can maybe look at u substitution as well. So the exponent is 3x plus 1, and of course the derivative of 3x plus 1 is 3, so we would want that 3 to be part of our integrand, and it's not. And so this would be one way we could do this. We could say integral of 3e to the 3x plus 1 dx. Just multiply the integrand by 3. Of course, we are not allowed to do that unless we make an adjustment to the outside. So I'm going to multiply the outside by 1/3. So now, inside the integrand there, I have exactly that e to the u du pattern, and so I can integrate. So it'll be 1/3. And keep in mind that the 3 right here, this 3, will just go back inside. And so we end up with e to the 3x plus 1 plus c, remembering that the antiderivative of e to the u du is just e to the u. If we wanted to do u substitution, that would be a little bit of a different technique, but it'll lead to the same answer. I would say u equals 3x plus 1. Remember, we want the u to always be the inside function. Du would equal 3 dx. And then as I tried to substitute, I would get e to the u. And then I still have the dx in there. And so I would, as we've typically done in the past, I would divide everything through by 3. I guess this is one way. We haven't always done it this way, I suppose. But the 3's would cancel out, and I'd see that dx equals du over 3. So I could write integral of e to the u times du over 3. And I could pull the 1/3 out, so it would be 1/3 e to the u du. And this would put us exactly in the form we talked about earlier. So we'd get 1/3 e to the u plus c. And then I would just need to plug back in the u. I'll just come up here and do that. So it'd be 1/3 e to the 3x plus 1 plus c. And we can see that it's the exact same answer we got before. Definitely more involved, right? But it's a good set of steps that if you prefer those, you can certainly do that. For the most part, I'm going to look for the pattern. I'm going to look for, did Timmy mess up the chain rule and can I fix it? To me, that's faster, but u substitution works extremely well also, just a little bit slower. Okay, number 2. The first thing I see in number 2 is that constant multiple of 5. I think that should come out. It'll make things a little bit more clear, perhaps. So I would write this as 5 integral x e to the negative x squared dx. And clearly the main thing going on here is the e to the negative x squared. And so what I want to check to see is the derivative of the exponent one of the factors in the integrand. So the derivative of the exponent would be negative 2x. And I look at the other factor, and the other factor is just an x. And so we do not have the pattern that we want with the chain rule. Timmy messed up the chain rule, so we need to fix it. It's pretty easy to fix. If I just turn that x into a negative 2x by multiplying by negative 2, I've got it. But I'm not allowed to do that unless I also divide the outside by negative 2, and so I need to do that as well. Once I do this, I have the exact chain rule pattern that I wanted. This negative 2x will simply go back inside to the exponent. So as I integrate, I get negative 5 halves e to the negative x squared plus c. And that's it. Again, if you have any doubts about any of these, you can certainly just reverse this whole process by differentiating and see, hopefully, that what you end up with is exactly the same thing that we started with for the integrand. Okay, we got one more example to do. It's number 3. Okay, so with number 3, we see once again we've got e to the u, and so we want to check. We want to check to see, is the derivative of that exponent the other factor in the integrand? And so the exponent is cosine of x. The derivative of cosine is negative sine, and so we don't quite have it, right? U prime equals negative sine of x. We look up here in our integrand and we just have sine of x. But this is a pretty easy one to fix. If we just multiply the inside by a negative 1, we would get negative sine of x times e to the cosine of x dx. We have it, but of course we can't do that unless we also balance that out by multiplying the outside by negative as well. And so at this point I do have the perfect chain rule pattern. This negative sine x is simply going to integrate back inside, and so I end up with negative. This negative right here stays. So negative e to the cosine of x plus c, and I've got it. Okay, so I hope that all worked out for you. We'll practice all of these when I see you next time in class. Have a great day.